Excited to talk today about work we've been doing at Quantsite and Quantsite Labs called uarray. I'm actually going to present the work of Hamir Abbasi, who isn't able to be here today, but he wrote much of the materials of this talk. I'll start by motivating a bit of why we've been doing this work, kind of what's behind it, what we're trying to accomplish, and then talk about the work itself and how far we've gotten. And there is actually a thing. So last year I was kind of rallying about a thing, and now we have a thing. So, you know, sometimes the things I'm trying to create do get created with wonderful people like Hamir and others at Quantsite Labs that make it possible. So uarray, separating interface from implementation. And we have a major problem. I talked earlier today about a major problem with extending Python in general that we have to solve. We have another major problem in NumPy land that we have to solve that's going to cause technical debt and cause major challenges for us going forward. And it's starting to emerge. It's something that's been uncovered as we have our friends at Google and Facebook and others build these amazing deep learning ecosystems that sort of have other implementations of NumPy. So I'm going to talk just a little bit about that first. We'll come back to this set of slides. So the joint talk between Hamir and I, we're going to talk a little about a brief history of NumPy. So uarray is an implementation. It's basically NumPy made an interface, made an implementation. So if we look at NumPy, and Jim Fulton, he gets on me a little bit for showing this because he feels like pretty imposter syndrome, like, why are you putting me there? But in 1994, you go back and look at the mailing list, you can see his matrix.py that he shared. And I mention this because sharing your code leads to good things. You don't know what it's going to lead to. In a very direct way, Jim Fulton's work in sharing matrix.py led to NumPy. So you never know what's going to happen, so share your work. Don't be afraid to put it out there and let people see it and learn and educate themselves and grow from it. So Jim Huguenin did the bulk of the work in getting NumPy started. As a graduate student at MIT, he wrote Numeric. And I heard that a few times. People have been in the community long enough to understand Numeric and Numarray. NumPy didn't come in a vacuum. NumPy emerged from existing code that existed. And that's been the beautiful thing about open source. Lets us build on each other. But Numeric didn't quite do some things that the Hubble Space Telescope needed as they were going to depend on Python for their image processing. So they worked on something called NumArray. Early days, I enjoyed talking to Perry and Rick about that. But the challenge was, what happened, it started to split the community. And as a SciPy author, I loved the SciPy community. I loved how it was bringing together a group of people sharing code and sharing ideas to do computing with Python. And then what happened with NumArray is that there are now people using libraries that only work with NumArray and other libraries that only work with Numeric. And we were kind of building this fractured community early on in Python land. And that really bothered me. So basically, NumPy was created to unify the array objects in Python. That history is sometimes lost. It was my early history of why I actually started the SciPy project. SciPy was my baby. It started way before NumPy in 1998 really. NumPy came in 2005, 2006 as a reaction to helping this community merge. And instead of writing papers and grants, I wrote NumPy, and so my tenure committee thought I didn't do enough work, and effectively I didn't get tenure at a university because I wrote NumPy. But we had this massive community success, so I'll take that. I definitely would trade that again. Now the reason it's successful today is not just because of my work, because of thousands of other people who both used it and contributed to it and made it part of their own. It's a very social effort, and it started as a social effort. I can go into detail about those interested in knowing how did NumPy really come about. But it was a lot of personal effort too. There's a lot of work that had to be done. It's a big community effort. Fast forward 12 years now, especially with TensorFlow and PyTorch and MXNet, there's actually array objects everywhere. There isn't just one NumPy array that everybody builds on. TensorFlow doesn't build on NumPy. It borrows the ideas, but it doesn't build on it. It uses the name dtype, but it has its own concept that's actually anemic. But they basically do a bunch of things new. They have, there's paddle, there's dynet, there's a bunch of things that are out there that are not NumPy. And that's okay, but we basically have a divided community again. It actually makes what I did, and you had this nice problem of unifying Numeric and Numarray. That was cute what you did. Now we have this massive division that's happening. And it's a bit frustrating, but it's also an opportunity. And the real problem isn't the fact there's lots of array objects. That's okay. A lot of array implementations can be a good thing. It's the fact that people are building software that requires one or the other. So hey, you're an Edward user. Oh, that's fine. Now, fortunately, back in the day, we actually created something called the buffer protocol. We fixed it twice. There's an old principle of if you find a problem, don't fix it first. Don't just fix the proximate cause, fix the ultimate cause. And back in the day, we didn't just write NumPy. We also created the buffer protocol so that anybody could actually share data So you wouldn't actually at least have to copy data back and forth between the objects. And so that helps us today, because you can actually today use a PyTorch object. It's not perfectly true in all cases, but where people are using the buffer protocol, you can actually use a PyTorch object and then put a NumPy wrapper around the same memory. And so that's okay, and especially when you're talking about gigabytes of data, that matters. But we're still having API sort of divergence, and people aren't able to write to a common API. So they basically have to choose their array object in order to build an array, build on top of it. All right, so what, if anything, should be done about this? Do we sacrifice tenure for 10 people? Is that what's going to require? We just, with this bigger problem, we sacrifice tenure for 10 people instead of just one. Something has to be done, or something could be done. It's an opportunity to make the world a better place. Well, we had the buffer protocol. So how do we extend that effort? And then the other thing we did, though, was actually a protocol approach. We built something called Dunder Array Interface, which allowed anybody to share. Even if the buffer protocol didn't exist, you could, as an object, export your memory through this array interface, and we did that too. Back in the day, some may remember Matplotlib. Matplotlib actually had a project called Numerics with an X. And for a time, NumPy was going to be called NumeriX, except for there was a piece of software out there called Numerics that it conflicted with. But it used, so when Matplotlib existed, early on, the way it solved the problem is instead of importing numeric or importing NumPy, it imported numerics with an X. And then it lets you choose which one of those, which backend you're going to pick. And so basically we took that idea and kind of said, well, let's generalize that to an array interface and kind of do that at the same time. That's there, it exists. It's starting to be rekindled with the CuPy. CuPy now has a CUDA array interface. There's some work in that direction that's happening. But this early protocol work actually has been happening as well, just not as, the buffer protocol actually was a lot of work, and a lot of people did a lot of work to make that possible, which is fantastic, because today you can actually now, a database programmer in Python, you don't have to depend on NumPy. You can actually just export a memory view, and NumPy can easily absorb that data without copying it. So it's a very valuable tool that's in Python today. But we can go back and revisit these efforts. And in fact, some of you, I won't talk today about XND, but XND is effectively a generalization of the buffer protocol, particularly around the type system, the data type system, and it's actually a very sophisticated story around that. It's very nice. The code works. It's out there. It's a set of C libraries. It's a reference implementation of a concept that basically generalizes the buffer protocol. But then the array interface, we thought, what if we could kind of generalize that and make a interface to functions that need to be called on objects. So you didn't have to decide what implementation you were going to use. So that's what motivated uarray. Uarray was like, what do we do to actually help the problem of effectively multiple dispatch? The problem of I'm a library writer writing scikit-learn, or I'm writing scikit-image, or I'm writing a linear algebra algorithm, and I know I need an array, but I don't really care if it's a strided pointer. If I don't care if it's actually a NumPy array, it could be a PyTorch array, it could be, as long as it has a certain interface, that's all I care about. Can we do that? And then have functions that will then just dispatch to the different implementations as needed. It should be easy, actually. This is Python, after all. This should be straightforward to do. But it's not done like that. Part of it is not technical, part of it is social, part of it is because of so much dependency, part of it because NumPy was so darn successful. Now everybody uses it. And so, but it is an implementation at the end of the day. It's not an interface, it's an implementation. And it doesn't have its interface is not super well defined. So let's talk about some of the challenges that exist. So many are familiar with Python 2 to Python 3 transition. How many use Python 2? How many actually do know about the Python 2, Python 3 transition? So that's kind of, I actually started NumPy, and part of my strategy to get adoption with NumPy was to make it Python 3. That's how I got Guido's attention. Was able to go to lunch with him in San Mateo, and I got him to come meet with me in Paul Dubois to talk about how do we make NumPy happen. And part of the strategy was to say, hey, we're going to make this Python 3 thing. And I did not realize that Python 3 would sort of take 10 years fast NumPy getting done to really work. But that's how we got their attention and got the attention of making this part of it. But Python 3 had a major problem. The major problem Python 3 had was the way strings were used in Python 2. If you were a user of string interface in Python 2, you'd write code and you didn't know if the person who wrote that code meant to use a string or they cared about the bytes. Because strings and bytes were exactly the same thing in Python 2. And even if somebody wanted, there was no way for them to say. There's no space for a code author to say, actually, I want to use this collection of this string I'm using is actually a bytes. Now, you could say B. People could start to say B, and they could start to use the B strings and U strings to indicate Unicode and bytes. But the code that was the hardest to translate, and I think it's twisted, is still very difficult to translate, was code that used that intrinsically. Very difficult to move forward. That was one of the key difficulties of actually moving the community forward, was that string bytes confusion problem. So I submit we have exactly the same problem in NumPy that's emerging. And it's in the following way. And I'll bring up Hamir's slides now. So this talk really give a lot of credit to Hamir. I'm here just representing some of his work. Let me see, present, there we go. And he's done a good job of sort of talking about uarray and what he's produced. But Hamir Abbasi, he works at Quansight Labs, software dev. He's going to talk about uarray and NumPy, and you can find him on Twitter. You can also find him at Quansight. He's got a Abbasi at quansight.com. So NumPy breaks this principle of separating implementation from interface. So a lot of people want to use, what they want is they say, oh, scikit-learn, and I get this, people got this question a lot. I want to use scikit-learn on GPUs. Well, can I just make that happen? Can't you just make a version of NumPy that works on GPUs and have scikit-learn automatically use it? Theoretically, maybe. But scikit-learn goes off and imports SciPy, and SciPy imports NumPy, and it uses NumPy as an array. But what you can't tell is, did the author of SciPy, of that particular module, linear algebra, did it mean to use NumPy as an array that implements slicing and get item? Or did it mean to use an array that's implemented as a pointer with strided memory of a particular type? You actually don't know, because there's no way to tell. NumPy is what it is. It's not, here's the interface to arrays, and then here's the implementation that's NumPy. There's no separation there. I think that's a major problem. And right now, there's some work going on in the community to say, well, kind of do a one-over on people, like, well, we'll kind of shift in this ufunc protocol concept that lets a Dask user or a SciPy user automatically have Dask arrays flow through that workflow automatically. And I think that'll work until it doesn't. And then when it doesn't, it'll just crash and burn horribly, and we'll basically be stuck. So I'm very nervous about that approach, and everyone knows, the NumPy community knows I'm nervous about the approach, but it's fine. I don't know everything, and it's fine to do things that I don't know about. But people are experimenting with that approach, but fundamentally, I think this is the wrong approach. I think we absolutely have to separate interface from implementation. There are things working in that direction that I'm excited about. I think people are starting to think about, well, let's see if we can't make an API. uarray is a solution. So one of the things I like to do, I don't like to complain about things. I like to actually say, well, here's a proposal. Here's something instead. Here's an idea. And that's what we're doing. With uarray, it's here's an idea. Here's another approach. Here's a way to separate implementation from interface in a way that we believe could go farther. As the ecosystem grew, it's kind of, NumPy is a victim of its own success. Lots of people used it. But it's also a victim of lack of funding. So as a lot of people were using NumPy, at the same time, I was not able to continue working on NumPy. I had to get a job. I had to go work for that job. I had to kind of keep, and I'm still in that situation. I have to provide for my family doing things other than project manage NumPy. Then we'll look at, then help NumPy move forward. That's kind of a major problem we have in the community, I still think. And a lot of issues we have in SciPy, NumPy, Pandas, and beyond are because of that fundamental fact. The people that work on those code and make them successful can't actually continue to work on them. They go get hired to do something else instead of actually continue to help those projects grow and become successful. So lots of people adopted it, and segmentation starts to grow. And what happens is segmentation started to go, so things like Dask, Xarray, CuPy, Sparse, Chainer, PyTorch, TensorFlow, they sort of started to mimic the NumPy API, parts of it, not parts of it, and a lot of users downstream would use it and then sort of expect usage of the NumPy API. But what end users really want is they want to be able to say, yeah, I can write this high-level library using a logical array and just have it work with any logical array that implements that interface. So that, yeah, as long as I have a backend that works with that array interface, I can use GPUs, or I could use FPGAs, or I could use a distributed cluster. Distributed, maybe the API has changed a little bit, because distributed has some intrinsic parallelization questions, but certainly GPU is an example of a distributed system. So shouldn't these be code compatible? Shouldn't you just be able to choose the implementation separately from the API? Right? I submit we need to be able to enable that. You need to make it intentional. And I'd love this to be a NumPy, actually. If NumPy itself just had, somebody could say from NumPy.api import, so that people know that you're actually using the API, not you don't care about the implementation. As opposed to currently, you don't know. If somebody imports NumPy, you don't know if they just care about, what do they care about? Which methods do they really care about? So that's what we have to fix, I think, fundamentally. It's downstream libraries that have to be able to tell us what they mean. So some adopted the NumPy interface without changing the implementation. Others did their own thing. A lot of people doing some of their own thing. But if NumPy was cleanly separated to interface to implementation, what would have happened? I think different things would have happened. I think there was a chance, and I'm sitting there remembering growing the API, but remember at the time, the API also emerged as a unification of two other libraries. So NumPy's API is big because it was solving a problem of bringing two communities together. So it had to kind of be big enough to support both those communities. But that doesn't mean that's the API that everybody should be building on downstream. And what we needed to do as well is create kind of, here's the array interface that downstream library authors can depend on. And that's the work we didn't do, which I think we can, what can we do now? Can we get unstuck? What's the answer? And this is a common problem in open source, actually, is things get there because of lots of reasons, and then people use it, and they're like, okay, what do we do now? In a larger organization, we refactor, we put investment resources into it, and we build on top of it. Where is that going to come from? And this is one reason I care so much about funding of open source and connecting companies and the money being made to the open source community, because I see problems that have to be fixed, and I don't know how to fix them without resources, without budget. So can we get unstuck? So we build an abstraction, right? There's no problem that can't be solved by another layer of indirection, right? I don't know who said that, but it's true. It's actually true. But it can be slower that way. I like this quote too. Hamir put this in. The purpose of abstraction is not to be vague, but to create a new semantic level in which one can be absolutely precise. And that's what we're trying to do. Put a semantic level in where you can be very precise about what you mean. So what's happening now in the NumPy community is there's something called array ufunc, which started as NumPy ufunc and said, hey, I want to build a ufunc. Can I just do this dunder protocol thing? And that kind of works okay. Part of the reason that works okay is because ufuncs are a smaller thing, that not many people use them. That's pretty straightforward and limited as to what the API looks like. So now you could overload, and you can overload, now you as an array implementer can implement this dunder array ufunc, and then all ufuncs in NumPy will defer to you and call your dunder array ufunc. It's actually a reasonable approach. It wasn't my favorite approach. Like my preferred approach has been for a few years that we just implement proper multi-methods. We just implement a proper abstraction mechanism to actually register functions with multiple implementations based on the types it's called with. If you think about multi-methods, what they are at their core, multi-methods are object-oriented programming lets you create an object and then have methods that are called. And if you think about what ends up happening, if you instantiate another object and call its method, you're having single argument dispatch. You're dispatching on the first argument, which is self, to the method to call. And you're calling a different method based on the object that's instantiated. So it's single argument dispatch. That works great until you have, well, now I'm going to add two numbers. I have a left operand and a right operand, and I'm going to add those two concepts. Well, which one do I choose? If I have two different objects there, which of those two objects add method should I call? And Python has a solution to that with dunder methods, has radd and rmul. Okay, great, that's two. But now if you have 3 arguments, what about 4 arguments? What about 5 arguments? Well, the solution to that is multi-methods. Julia implements that, Dylan implements that. It's been implemented multiple times. There's some real challenging technical problems in terms of what do I do if I then subtype. Let's not get into that. I think for most people, it's a pretty straightforward thing to do to just think about registering an implementation for the types you insert. In fact, that's what NumPy does with ufuncs. Ufuncs under the covers are a multi-method implementation. That's how they work. How does NumPy know when you call add on an array of 2 integer arguments? How does it know to differentiate that? What machine code does it call? Differentiating that from calling add on float arguments. Well, it's a multi-method. You've registered a different implementation, a different kernel. Let's bring that up, and so that Python has proper multi-methods. Now, Matt Rockland did that. There's a package called multiple dispatch. There is a mechanism for this. It's one mechanism of many. But how do we make this more ubiquitous? That's the approach I would take. I would actually just have multi-dispatch, multiple methods be more ubiquitous in Python. There's some challenges with that. There's some challenges of, the biggest challenge is actually one of global versus local scope. If you think about a multiple dispatch mechanism, somewhere there's a table that's registered about where things get called. That's basically a global table somewhere. Like with object-oriented, that table is attached to the object itself. And so it's contained in that scope. Kind of a little better. So where do you put that table when you're talking about this kind of a thing? That's a good, there's some real questions. It can be attached to module objects. I mean, one approach is attached to module objects in Python, so it's contained in that module object. Anywhere that module is instantiated, it's a new thing. I think there are solutions to that, but that becomes one of the questions. It's a real deep question compared to, let me funnel things through a functional approach. And particularly when you start talking about parallelism. I start talking about, I'm going to run this code here, and I'm going to run this code over here. How do I make sure that when I'm running this code and it's got a particular multiple dispatch mechanism, I have the same code over here? Like I haven't somehow changed my module over here. How do I keep things contained? Those are fundamental questions, actually, in computer science that mean that people have different opinions about this, right? So one of the advantages of the protocol methods is protocols are attached to the object itself, so it's kind of all there. And some can argue that that's a better approach. So array ufunc is fine. That was kind of basically a plus 0.5 on array ufunc. Okay, that's fine, but would rather see multiple dispatch handled. Okay, it's not enough. Now we have array function. Array function tries to take more of the methods in Python, more of the methods in NumPy, things like array creation, things like linear algebra. Now you can do array function. Actually, it's been not enough. There's actually 4 or 5 more protocols that have to be there. And so what's happening in the NumPy community is they're trying to take the NumPy API as it is and kind of then protocolize it. I have several concerns about that. One of them is there's too many, the API is bigger, too big anyway. We should restrict that API and actually be intentional about what API we're going to make an interface around, not just kind of what's there because of history. Let's actually be intentional and create an array API that makes sense. And we have a lot of code out there to help us guide that question at the moment. And then more and more. So uarray is a different solution. Uarray is an implementation of this multiple dispatch mechanism and the ability to do coercion. It creates an abstraction, and you'll see examples of how it works in a second. Along with other goodies, you can basically, with uarray, create a version of NumPy that lets you switch the back end easily. You can switch the back end to GPUs, to Dask, to CuPy easily, and then have it all flow through. It follows this separation of concerns, and it makes it possible for NumPy to be an interface, at least on the Python level. There's another question about the C level of NumPy interface, so we have to see my ePython talk for how we're going to solve that. So here's an example of how it actually works. This is working code. uarray exists today. It's not just an idea. ePython is just an idea. uarray is not an idea. It's a real code. It works. You can go download it, install it, start using it. So there's uarray and then there's uNumPy. uarray is kind of misnamed, really, because it's really uarray is really udispatch. uarray is a way to build multiple dispatch mechanisms for anything, not just arrays, but for anything you want. So, okay, but kind of historically it got named uarray. So uarray lets you set a backend to a context. So within this context, all the code in uNumPy now dispatches based on the Dask backend. Right, so import uNumPy as NP. A lot of people do import NumPy as NP. If you just import uNumPy, so a couple things. First of all, you're intentionally saying I'm actually looking for the interface to NumPy, not NumPy itself. So you're not saying import NumPy and pretend that it works with Dask. I'm saying import uNumPy and tell people that actually you are trying to use an array interface and not just an implementation. And now set a backend. The default backend for uNumPy is NumPy, so if you don't set a backend, it'll assume you meant NumPy, and off it goes. But you can set a backend, and now np1s returns a Dask array, and you can do anything with X, and it's Dask all the way. So that's how it works. You can also nest backends. You can have a CuPy array instead of a Dask array. So you can, with Dask backend, with CuPy, you can actually have a CuPy array of GPU arrays on Dask arrays. And that works too. Then the changes propagate all along down the stack. Now that's true as long as there's some C stuff under the covers. Again, but part of this is good. The goal, I think the work we still have to do is for the NumPy community to sort of create an API level that isn't magic. That is basically, this is an API that can be re-implemented. So currently, this you can also choose a backend for a submodule. Like if you have NumPy FFT or NumPy einsum, you can actually choose a particular runtime for that module, and you can change that. And it can all be done at runtime. And this isn't done by monkey patching. I don't know if you know what that term is. Monkey patching is the idea. Python's so generic, you can actually just go get the object and assign the attributes to something else at runtime. And you can do that. And in fact, the one example of that, there's a few examples that are pretty interesting, but gEvent does that to change all the I/O loops, to basically use before coroutines, kind of early age of use greenlets. under the covers. But by doing this, you can get rid of kind of evil monkey patching that a few other vendors provide, basically, that has made some of the community a little unhappy. So there's 2 protocols instead of like in the 20. So UA function, UA convert. UA function is how you actually build your, it's borrowing the ideas of array function, but instead of forcing it through NumPy arrays, it's allowing you, because you've defined a new interface, you can do a lot more, and you're not constrained. And then also you're communicating correctly to users who, anybody using NumPy is telling everybody they care about an interface, not a particular implementation. All right, so what if you could do something like this? Use just like NumPy with no backend, without switching. So there's basically been some work. The uarray is currently working code. It works. It's actually used for SciPy's FFT module. In fact, there's a Python implementation, then a C++ implementation of uarray to make it faster, and that version is used by SciPy to allow the SciPy FFT module to switch between implementations of how it actually implements the SciPy FFT module. So it's working code, working today. Now that we've been talking to the NumPy community about how, okay, how does this help the NumPy problem? Could it be used? Could NumPy depend on it? And appropriately, that's a big, deep question, and there's a lot of debate going on about that. And it's good debate. It's really getting, it's led to some really interesting conversations. One thing I really like about that's led to recently is NumPy starting to really think about, okay, maybe we just need a NumPy API module, or a module that allows people to indicate that they have an interface they're trying to do. So there's a NEP actually that's being discussed. So that's uarray. Happy to take questions. Talk about. We have about 15 minutes here. Gosh, it would be a great time for a demo here, but I don't have one. That's what happens when it's Hamir's code and Hamir's laptop, and he's not here to give it, but he would give a beautiful demo that shows how to use it. But that's the idea. The idea is it really intended to be very simple for SciPy. The idea would be SciPy and Scikit and other users, downstream users, would use uarray, would use NumPy in particular, instead of NumPy, if they want to indicate they're caring about an array interface and not particular implementation. All right, so look for more work in this direction. If it's uarray, high-level APIs, like going forward, I would say uarray is here. It's a multiple dispatch mechanism that works. It's being used by SciPy, so it'll continue. How far it spreads will kind of depend on the next several months. 12 to 18 months. A lot of work is being done into, okay, how do we, we're working with Intel and a few other vendors to talk about high-level APIs for arrays, data frames, and data types. That may use uarray. It's not guaranteed we're going to use uarray, but we might. I mean, it's basically, we're trying to make that separation a real thing. And so that's the other initiative you'll see on Open Teams, is that effort to really unify array computing and data frame computing around APIs as opposed to instead of implementations. So that's the next really 2 years of work, of innovation work at Quansight will be around some of that. So, and uarray fits into that category as a particular implementation. Yeah.
So you actually started answering my question. You actually started answering the question, but I want to continue and go deeper into specific examples of applications of what you think might be possible, if you're allowed to talk about this. I know that some things are maybe delicate.
Oh, I think I'm allowed to talk about any of this, yeah.
Okay.
I probably just can't mention names yet, but I can definitely talk about the ideas.
Please do give us more examples so we can visualize it better, how impactful it will be, because...
It's a good question. So for you as an end user of pandas, you probably won't see it, right? You'll keep using pandas, but what you'll notice is suddenly GPUs work. Suddenly I can migrate to new runtime. Suddenly it's not, oh, hey, I've got this cuDF. Like right now what's happening is we have new implementations coming out. Hey, I'm working data frames on GPUs, and it's a whole new namespace, right? Oh, so if I want data frames on GPUs, that's suddenly a different namespace? Why is that? We're kind of going backwards a bit, where, back to the days of, oh, I've got new hardware, I got to write a different computing language. I can't just, have all these different libraries to import. This had happened back in the C days. I wrote C code and it was supposed to be cross-platform, but it couldn't actually target new hardware unless I used these particular includes, this particular set of libraries. We're kind of getting there in the Python world where, oh, I want to use GPUs, I've got to use cuDF, or I've got to use cuML, I can't use scikit-learn. That's not ideal, because as an end user, that's an implementation detail. Where it runs and how the compute works is an implementation detail. So this is in the spirit of that. You as an end user, very likely, I don't imagine you'd ever use uarray or uNumPy, right? Because you might, actually you might if you're basically wanting to write, sorry, that's not true. You might write a script that uses uNumPy if what you want to do is write a script that says, I want to use an array interface. And then I want to try it with Dask, and I want to try it with GPUs, and I want to try it with, I want to try it with anything. You might. Today, that's what you do, is you'd use uNumPy, and if we had a upandas, we don't yet, but upandas would basically be like, import upandas as PD, and so you still use the same API you're used to, but now you know that the implementation can be different, and you're not having to deal with those consequences. It allows library authors, allows the back-end generator, you're just waiting for someone to write that back-end, and as soon as they do, it's off to the races for you. So if NumPy had been built with uNumPy, that question I got all the time of, can I get scikit-learn working on GPUs? I could have said, yes, that'll be a weekend, and we'll get that working. It's getting, like today, with array function, and the fact that CuPy has array function, and that scikit-learn is getting there to use SciPy functions with array function, you can what I fear is the demo will work. And people are successfully using the array function today, and it's working to some degree. I would personally hesitate to tell someone to put that in production and rely on it. That's where I'm at. And so this is something I could comfortably build and say something this will work, and we can make sure this works. And we're not going to have funny corner cases everywhere. But that's a debatable question right now, and that's currently the conversation that's happening. I do think ultimately we're going to have to think hard about the namespace. I'd love to see NumPy as the namespace continue, but it's already not continuing because we have TensorFlow, Torch, and others as namespaces that people are using arrays. So for me, the pandas namespace I think is safer because it's going to be easier for us to use this technology under the covers in pandas, because pandas already is a high-level interface. So for example, as an end user, it's hard to say. It's still very early. Today you can use uNumPy if you'd like. It works, and it's a very straightforward piece of code. It's not a complicated piece of code to support. We're going to keep supporting it for the SciPy use cases. All it needs is backends, and those backends will be generally applicable to other code bases as well. So it's not like you're stuck. I don't know if that helps, but it's a little bit, actually writing a backend is a little bit confusing. I mean, it's not like it's super easy. I would say the interface to write a backend is still meant for computer scientists. I have some really brilliant engineers at Quantsite Labs, and I love them, but sometimes they build interfaces that look like they're built for other computer scientists. Yeah, I'm kind of the litmus test because I'm a scientist from the heart. If I look at something and go, yeah, I have to put on my computer science hat to understand what you did there, maybe we can do better. Maybe we can build a better interface that makes it a little easier to communicate what we're talking about. We're still working on that, I would say, but it works today. What's there works, it's capable, and there's actually a really fast C++ implementation as well. So if you look at API authors, it's not too bad, but effectively you have to generalize the concept of I have this function if I want to have a function I want to make a multi-method, I have to kind of abstract the concept of the function and have an argument extractor, argument replacer, and I have to kind of think at a high level like that. You can implement this UA function, UA convert, or the two ones, and you can see UA function takes a signature method args keyword. Args basically takes the concepts, and then there's some examples here, but so that's uarray. Uarray is one of several projects at Quantsite that are in this direction. Later, I think tomorrow, Saul will be talking about a concept called meta DSL, which actually takes this and goes one step up to the AST level This is, let's call it immediate mode. You're basically working, you have an object, it dispatches to an implementation, and it's happening immediately, using the syntax of Python, using the Python runtime. MetaDSL is about using the syntax of Python, and then inserting and capturing as the syntax is created to rewrite what it calls. It actually is a higher level, and it's more powerful because of that. A little harder to understand, but it lets you, I relate it to the graph mode. TensorFlow and PyTorch have both introduced immediate mode and graph mode. uarray is a multiple dispatch mechanism on the immediate mode. MetaDSL is a way to dispatch different runtimes at the compile time, at the AST, abstract syntax tree level. So you can basically, this syntax rewrites to anything. It's quite a bit more powerful and lets you do interesting kinds of things like target the IR, MLIR, lets you target all kinds of runtimes, lets you target new runtimes, not just new functions. So we've been doing a lot of research in this direction to see how to solve this problem at a fundamental level while also integrating with all the tools that are out there, because the community is spread. There's a lot of cool tools out there that we want to make sure and take advantage of. The whole goal is to reuse what's there, and not to rewrite the world, but to reuse. And how do we do that? And still make the experience seamless for the end user, or as seamless as possible for the end user. So that's the general goal. All right, well, thank you. Appreciate it. I'll give you some time back, but let me know if you have any questions, and I can pass them along to the team, and we'll let you know. Thanks.